In this video, we'll explore the evolution of software architecture, from monolithic to cutting-edge microservices. We'll dive into the impact of Conway's law and understand different architectures like event-driven, serverless, and CQRS. So let's get started. As we step back to the late 1960s and early 1970s, we find ourselves in a transformative period when the inherent importance of a software system's structure was first acknowledged. This recognition paved the way for the evolution we witness today. Back then, software development birthed applications as singular entities known as monolithic. This simplicity facilitated development, testing, and deployment, but presented challenges like lack of separation of concerns and interdependencies. Fast forward to the 1980s, the era of personal computers and networks introduced the client-server architecture, which was a pivotal shift. This era embraced the dual structure of the user interface on the client side and data processing and business logic on the server side, which offered more flexibility and scalability. Yet, the interdependence between these components limited true modularity. As we progress into the 1990s, a new wave emerged with the 3-tier and N-tier architecture. The layers presentation, business logic, and data fostered flexibility and scalability. However, in practice, these layers were often tightly coupled and still deployed as a single unit, which is why the 2-tier and 3-tier and N-tier architectures are considered monolithic. To solve the coupling challenge, we've witnessed the appearance of microservices architectures. But the truth is that there is another reason behind the birth of the microservices paradigm. To understand this reason, we need to have a look at Conway's law. Melvin Conway, the author of this law, stated it as follows: any organization that designs a system defined broadly will produce a design whose structure is a copy of the organization's communication structure. This means that the size and physical organization of the teams working on a project influence its architecture. As an example of this, I can mention the Otto company in Germany, which has a huge e-commerce platform and many teams work on it using microservices. After this insight into the intricate relationship between organizational structures and architectural design and the contextual understanding of the emergence of microservices, let's see a comparative analysis to discern the nuances within these architectural patterns. As a specific type of microservices, we will focus on event-driven architecture, serverless architecture, and command query responsibility segregation, or CQRS architecture. These approaches offer unique solutions to challenges of system design and provide distinct benefits and consideration. In an event-driven architecture, services communicate with each other by producing and consuming events. Events represent significant changes or occurrences within the system. Each service can react to events it's interested in and perform its own operations accordingly. This approach offers loose coupling and scalability. In a serverless architecture, also known as function as a service or FaaS, each function or microservice performs a specific task or business logic and is deployed and executed in response to specific events or triggers. In a serverless architecture, the focus is on deploying and scaling individual functions or microservices independently. On the other side, CQRS is an architectural pattern that separates the read and write operations in a system. It involves having separate models for reading and writing data. This concept of separation between read and write operations and services requires from someone who worked for a long time with the other architectural paradigms, regardless of whether they are monolithic or microservices, a bit of cognitive load and a new thinking pattern. So let's have a look at it with more details. CQRS pattern has gained attention in recent years. Its concept was first introduced by Greg Young, and it has become popular in the context of domain-driven design and event sourcing. Greg Young, by the way, is a prominent figure in the software architecture world. He is known for his contributions to the concept of CQRS and event sourcing. His insights reflect a deep understanding of these architectural patterns including their practical applications and potential pitfalls. In CQRS system, each microservice focuses on its specific responsibility, providing clear separation of concerns. It's also possible to have separate databases, a write database used only for making changes, this is known as the command side, and a read database used only for reading the data and creating materialized views. This is known as the query side. Let's imagine now that a platform like YouTube is built with the CQRS paradigm. In this case, when a content creator uploads a new video to the platform, it will be processed by the command service and saved in the write database. After that, a synchronization between the write and read databases will be triggered in order to show the viewers the newly uploaded video when they open the YouTube page or the appropriate YouTube channel. In this simplified example, the blog post service represents the write model responsible for creating, updating, and deleting blog posts. It uses the blog post repository to persist the blog posts in the database. And here we see the blog post query service, which represents the read model responsible for querying and retrieving blog posts. It also uses the blog post repository to fetch the relevant blog posts from the database and converts them into DTO, or data transfer objects, for representation. In a real-world scenario, you would likely have more complex business logic, error handling, and additional layers, such as controllers and DTO mappings in your application. One advantage of the CQRS paradigm is that it adds a new dimension to your system, which is time. When we follow and analyze the sequence of read operations and write operations over time, we can build the state of a system, which is more challenging to have with other architectural paradigms. The funny thing here is that state management patterns are relevant at different levels of an application or a system. UI frameworks like Angular or React offer different mechanisms for managing client-side status. If we zoom in, we can see that the UI state management and front-end reactivity model is similar to the event-driven architecture pattern. The difference is that in modern front-end development, instead of microservices, we have micro-frontends and UI components. And instead of Kafka and AWS simple queue service, we use state management with Redux for React applications, or libraries like NGRX or NGXS, or behavior subject-based services or signals for Angular applications. I find this fact very fascinating because it reminds me of the repeating patterns in nature, like fractals. But let's come back to the time dimension that I mentioned with the CQRS architectural pattern. For a better understanding of this dimension, let's take the invoice entity as a case study. An invoice could have a status draft, created, signed, paid, or closed. Classical architectural patterns typically use a status attribute to manage entities' status. In contrast, event-driven architecture leverage asynchronous event-based communication to notify interested components or services about status changes. This way promotes decoupled systems and enhances scalability. CQRS further refines this by separating the modification and reading of an entity status. When paired with event sourcing, CQRS allows system to maintain richer historical context of changes. Every update of an entity status can be captured as a distinct event with its timestamp. This not only adds a clear time dimension of data changes, but also enables complex temporal queries, such as tracking the history of status changes over time or reconstructing past status of an entity. Thus, CQRS inherently introduces a time dimension to system design, emphasizing the temporal aspects of data consistency, the processing of commands and queries, and the historical tracking of changes. This temporal consideration is crucial for designing systems that require robustness, scalability, and detailed auditing or historical analysis capabilities. Excited about diving deeper into the world of software architecture? This video is just the beginning. Check out my Udemy video course on software architecture, where I explore these concepts further and dive into real-world challenges. The link to the course is in the video description below. And here is a bonus. Subscribe to my newsletter and you will get free access to all my courses. If you found this video helpful, don't forget to hit the like button and subscribe to the channel for more updates and tech insights. See you next time.